a small recapitulation of the previous class that we have done, that is the momentum transfer, how that is being done for a particular component, that is or velocity component, that is x component of the velocity Vx acting on the x, y and z directions by the bulk transport as well by the molecular transport. You remember we said that the molecular transport is being done by the molecules of the layers which are vibrating in, staying in the layer, but they are giving the energy or they are exchanging the energy with the adjacent layer molecules, right. This way the two ways of transport of momentum occurring we have done for the one component, that is x component. Now we will do for y and z and then sum up all of them and derive the basic equation of motion, that is the Navier-Stokes. Okay. So, let us follow. So, then we had come, if you remember, we had come up to this, that accumulation, right, where the volume element was there, del x, del y, del z, and we also had taken that by molecular transport, by the bulk transport. This was for molecular transport, this was for bulk transport we had done, right, and then pressure term and the gravity term, that is some of the other forces, right. So, now if we divide in both the sides with del x, del y, del z, right. If we divide with del x, del y, del z, dividing both the sides, we can write that rho Vx into Vx at x minus rho Vx into Vx at x plus delta x, right. This divided by del x, del y, del z, and we had on the top this, if you remember, that this was del y, del z. So, dividing it with del x, del y, del z, del x, del y, del z, we take off del y, del z, it remains del x, right. Similarly, here also del x, del y, del z, we take off del y, del z, or rather del x, del z, del y remains, and in this case also del x, del y, del z. So, we take off del y, del x, del z remains, right. Similarly, here also. So, dividing all with del x, del y, del z, we get respective terms like that, divide by rho x, right, plus rho Vy, Vx at the face y minus rho Vy, Vx at the face y plus delta y over del y plus rho Vz to Vx at the face z minus rho Vx, rho Vz into Vx at the face z plus delta z over del z, right, plus tau xx at the face x minus tau xx at the face x plus delta x over del x plus tau yx, right, tau yx at the face y minus tau yx at the face y plus delta y over del y plus tau zx at the face z minus tau zx at the face z plus delta z over del z, right. So, this is equals and plus the pressure terms, that is P at x plus delta x minus P at x plus delta x minus P at sorry, P at x minus P at x plus delta x. It should be clearly written P at x minus P at x plus delta x into or divided by, that was also we had del x del y del z. So, here it is del x. So, this plus in rho g, rather we had del x del y del z, if you remember. So, that goes up, so rho g x remains, and this is equal to nothing but del L T of rho v x, that is the accumulation term, right. So, this applying the theory of limit x del x tends to 0, and from the definition of applying this limit x del x del y del z tends to 0 and applying the definition of derivative, right. You know the derivative, that is out minus in over the del. So, this is the derivative. So, we can write then this is nothing but del rho v x del t, right. This is equals to minus del x of rho v x into v x, right, plus del y of rho v y into v x, right, plus del z of rho v z into v x, right. This minus del x of tau x x plus del y of tau y x plus del z of tau z x, right. This minus del p del x plus rho g x over this rho g x, this is equals to, rather already we have made it equal. So, this we can say to be a equation number 1, right. In this case, here remember that we have applied this concept that limit del x del y del z that tends to 0, number 1, and number 2, when limit tends to 0 and by the definition of derivative, this out minus in over delta, that is nothing but the derivative, that is del x of rho v x v x, del y of rho v y v x, del z of rho v z v x, right. Similarly, del x of tau x x, del y of tau y x, del z of tau z x, right. Here in this case also minus this, that is why negative is coming. So, del p del x, and here we had rho g x, all x y z was out. So, only rho g x remaining, right. So, this we can say that equation number 1, and subsequently we can write for the other two components, that is for the y component and z component, we can also write that similar to this del L T of rho v y, this is equals to minus del y of rho v y, right, rho v y or rather rho v x v y, rho v x v y, right, and this plus this is del t. So, del x of rho v x v y plus del y of rho v y v y, right, plus del del z of rho b z v y, right. This is for the bulk transport, and for molecular transport we can write tau del x of tau x y, right, plus del y of tau y y, right, plus del z of tau z y, right. This plus that del p, or rather here it will be minus because by definition. So, minus del p del y plus rho g y, and in the same way we can write the z1, right. We are not writing, then we will okay, it will take only just a little time. Del t of rho v z, this is equals to minus del x of del x of rho v x v z plus del y of rho v y v z plus del z of rho v z v z, right. So, this was like this plus or this plus, of course, that will come minus ultimately, right. Here it should have been minus, here also it is minus, right. So, del x and one negative this term. So, del x of, right, tau x y, or in this case it will be x z, right, plus del y of tau y z plus del z of tau z z, right. This minus del p del z plus rho g z. These are the three equations for the three coordinate systems, right. Now, if we remember, we had given this was the equation 1, right. So, keep in mind that this equation, then from that equation we can write del t of rho v x, right. This is again nothing but rho times del v x del t, or del t of rho v x plus v x del rho del t, right. Again this is on expansion u v we can write, right. So, this from equation of continuity we can write, from equation of continuity we can write that del rho del t, this is equals to minus del x of rho v x, right, plus del y of rho v y plus del z of rho v z, right. This was taken in the equation of continuity and we can write there. So, we can write then del t of rho v z, or rather rho v x is equal to rho times del v x del t minus v x into del x of rho v x, right, plus del y of rho v y plus del z of rho v z, right. So, this we can write, and if we remember the right side of the equation, which was, this was equation 1 and the right side was this big minus del x of rho v x, right. So, one term if we take, then we can write minus del x of rho v x, right, del x of rho Vx, right, plus del y of rho V y Vx plus del z of rho Vz Vx, right. This was like that, minus del x of tau xx plus del y of, this will be under bracket. So, del y of tau yx plus del z of tau zx, right. This minus we also had del p del x plus rho g x, right. So, this on further expansion we can write, this first term can be expanded like this, that minus rho Vx, if we take this as u and this as v, then minus rho Vx into del Vx del x, right, minus rho Vy del Vy del y plus rather minus, since we have not given any bracket, if we would have given a bracket, then we could have written like this, then rho Vz del Vz del z, rather del Vx del x, this is del Vx del y del Vx del z, right. This we could have written, and this minus Vx times del x of rho Vx plus del y of rho Vy plus del z of rho Vz, right. This term on expansion we can write like this, right, as u and v. So, if we do like that, then we can rewrite this equation 1 which we have shown you earlier as rho del Vx del t, rho del Vx del t, this is equals to Vx into del x of rho Vx, right, plus del y of rho Vy plus del z of rho Vz minus rho Vx times del x of Vx, right, minus rho Vy del y of rho Vy, right, and also minus rho Vz del z of del z of Vz, right. So, this minus Vx del x of rho Vx plus del y of rho Vy plus del z of rho V z rho Vx, okay, rho Vx. So, this also will be rho Vx. So, we can write, so del rho Vx del x, oh sorry, this is y and this is z, right, rho Vz. This if we write, then minus del x of tau xx plus del y of tau yx plus del z of tau zx, right. So, this minus del p del x plus rho gx, right. So, this we can write further that we can say that rho del Vx del t plus del x of Vx plus del y of Vy plus del z of Vz. This is nothing but tau del x of tau y xx, right, del x of tau xx plus del y of tau yx plus del z of tau zx, right. So, this we can write, and of course, here we can if we remember that earlier we had taken this, and course minus del p del x plus rho gx was also there, right. Then we can say that this to be nothing but the operand capital D. So, we can write that capital D Vx into dt times rho, this is nothing but minus del x of tau xx plus del y of tau yx plus del z of tau zx, right. So, this is so. This is for the x component. Similarly, for the y and z component, we can write rho the capital D operand del Vy del t, right. This is equals to minus del x of tau xy plus del y of tau yy plus del z of tau zy, right. So, this, and similarly for the z component rho d of v capital D Vz dt, this is equals to again minus del x of tau zx, or in this case xz, right, plus del y of tau yz plus del z of tau zz, right. So, these three can be written easily, right. Now, if we substitute that by using the value tau xx is nothing but minus mu del x of Vx. Del x of Vx is tau yx. Similarly, we can also write tau yx is equals to minus mu del y of Vx, right, and using the similar way all others different taus, right. You remember that this one and this one, okay, I have given two, okay, let me also give the third one tau z x y z, tau z x, this is equals to minus mu del V x del z, right. So, this is for the velocity component, this is for the direction, this is for the velocity component, this is for the direction, this is for the velocity component, this is for the direction. If we keep in mind this simple thing, then we will be able to expand it in terms of V, right. All these tau terms, that is your shear stress terms, we can expand in terms of the velocity terms if they are in tau xx, first x is the direction, second x is the velocity component, tau yx, y is the direction, x is the velocity component. So, that means it will be del v y del x, right, del v x del x then similarly tau y z will be del v z del y, right. So, keeping all these in mind, if we substitute them in this equation, because we some more, if we show that, for example this we can write tau this minus mu this, therefore we can write del x of tau xx. Tau xx is defined as this, right. So, del x of tau xx we can write, this is nothing but del 2 v y del x square, right, del 2 v del, this is tau not xx, tau xx will be del x of tau xx will be minus minus mu, right, minus mu into del 2 v x del x square, right, del 2 v x del x square. So, keeping all minus mu, similarly we can write del y of tau y x, right, is equals to again del 2 v x del y square, like that all the terms we can write with of course minus mu, right. And in that case, if we substitute them in the equation what we had shown as equation 1, if we substitute all these tau values in terms of velocity and viscosity, then we can say that rho times del T of Bx plus Vx del x of Vx del x of Vx plus Vy del y of Vy plus Vz del z of Vz. This is equals to that mu, now it has come to the right side. So, negative has gone out, mu del 2 Vx del x square, right, plus del 2 Vx del y square plus del 2 Vx del z square, right, minus del p del x plus rho gx, right. This is for x component. For y component we can write rho del t of Vy, right, plus Vx del x of Vy plus Vy del y of Vy plus Vz del z of Vz, right, or rather this will be Vy. This is equals to mu del 2 Vy del x square plus del 2 Vy del y square plus del 2 Vy del z square, right, minus del p del y plus rho gy, and for the z component similarly del Vz del t plus Vz del Vz del x plus Vz plus this is Vx, then Vx del Vz del y plus Vz del Vz del z, right. This is equals to mu del 2 Vz del x square plus del 2 Vz del y square plus del 2 Vz del z square minus rho rather del p del z minus del p del z plus rho g z. So, these are known as Navier-Stokes equation. When Navier-Stokes equations. So, when, and this is for the Cartesian coordinate x, y, z, right. Now, when you will be doing it, you have to identify from the problem given or from the situation which term corresponds to what. So, if you can identify, you can solve any problem on the momentum transfer with the help of this Navier-Stokes equation, right. We will do some problems next time and then identify and understand these individual terms. Okay. So, that is what here we do. So, Navier-Stokes equation in cylindrical coordinate I have given in the slide, you can check, and also this of course not coming proper way, there are component, theta component like that. So, thank you.